Welcome to Next Thermal's presentation on how to target heat to reach higher performance. I'm Jeff Wheeler, Vice President of Operations for Next Thermal Corporation. We're very excited to present this to you, and it's our hope that you find these topics informative. Sustainability initiatives are leading innovations in materials processing. System buyers, such as Director of Engineering for a major consumer packaged goods producer, are now demanding that the total cost of ownership of the machine includes the definition of energy usage. In many processes that use thermal energy, the cost of creating the energy is the leading operating cost in the production process. Using smart electric heating methods compared to natural gas or hot oil, the application can be targeted for best results and controlled more consistently. This is part 2 of a 4-part series that covers a review of parts of electrically heated system, the durability of an electrically heated system, how to increase efficiency, and finally a review of a case study of high-performance heater. This session will start with a review of what we mean by high performance when we talk about the use of electric heating tools. We will also review what durability challenges that electrical component endures in the environment of the tool over time. What do we mean when we say higher performance? Let's take a minute to define this in terms of heating of systems. Less cost means not focus on the total cost of operation of the heater and the tool. Saving energy and eliminating heat energy waste. Installing reliable solutions that lower service costs and allow for more uptime. Supporting lower count of service parts in stock. Fast delivery rather than spare parts inventory that consumes capital and ends up being lost anyway. Faster production means higher processing speeds, which allow for more production per unit of machine time. A lower scrap or defective product means more revenue per production run. More consistent output can also provide lower risk to packaged product for recalls or spoilage. Compared to other methods of creating thermal energy, electric heating is unique in that it's 100% efficient. With the range of heater sizes available today and the design flexibility that electric allows, it's possible to target where and how much thermal energy is needed for highest performance of the final system. All these points are topics we will touch on in the presentation. In part 1, we reviewed the various parts that form a thermal process and the roles of each. Here we will move into the topics of durability and the influences that we can make to provide a better product experience. Durability. An electric heater or sensor is designed to operate within a specific environment. In general, they are designed to be robust and reliable. However, there are some considerations that can extend the performance in life. Materials must be designed to withstand the exposed temperature of the surrounding area. That seems obvious, but there are other considerations to heat that should also be understood. For example, the thermal overshoot can result in a hotter than expected core temperature at a moment in time. System set point does not mean the core temperature of the heater or the exposure of the leads are the same. Heaters with a higher watt density and poor fit results in a high rate of rise and higher overshoot in internal temperatures. In the chart shown is an actual test using a customer's application. The customer was operating the tool at 350 degrees Fahrenheit, but had a high watt density on the heater and a loose fit to the tool. We were experiencing failures in the epoxy seal at the lead end that was rated to 500 degrees Fahrenheit. Even though the system was regulated by the control thermocouple to 350 degrees Fahrenheit, installing an internal thermocouple, we were able to show that due to the heater's very high watt density and poor fit condition, the core temperature of the heater was reaching 850 to 975 degrees Fahrenheit in under 9 minutes before the control thermocouple started clipping the power. During this time, it was exceeding the surface temperature of the epoxy, thereby damaging it. It is also important to note the difference between the set point, which is a green line, and the actual heater temperature in the steady state condition, shown as a blue line, is lost in the efficiency of the heat transfer from the heater being loose in the tool. And last, you can see the influence of both the high watt density and the loose fit of the mass. In the first 25 seconds, the rate of rise for the internal thermocouple. Some difference is normal on the rate of rise for the internal temperature of the heater versus the tool at room temperature, but you can also look at that as a waste in the system. As we discussed previously, since often the set temperature of the system is not the exposure temperature, the surface rating of the materials have to be considered. The good resource for wire rating is a NEMA WC 73-2000 standard. This covers high-temperature designs and reviews different alloy and derating strategies based on environment temperature, self-heating from current flow, bundling in conduit or open-air routing, and of course, derating based on length of the conductor. In-potting options at the lead end are chosen based on the required sealing performance at a maximum sustained temperature, and the contact materials such as elite wire insulation. In the next slide, we will talk more about the choices in potting. Heater sheath material is another consideration, as it should be fit for the temperature, prevent galvanic oxidation to the tool during use, or other environmental exposures. It is well understood that moisture inside of an electrical device such as a heater can be detrimental to their building safety. What is now well understood is that the insulation inside of a heater has high affinity for humidity. The seal materials that are chosen must be based on the exposure concerns. For liquid protection of high movement, silicone is a great choice. For humidity or gaseous exposure, epoxy is better suited. Both can be used with PTFE or PFA wires if properly treated for adhesion. However, it is important to note that any design that uses a swaged-in straighted wire that passes through the seal area cannot truly be sealed, as the wire strands will allow moisture or gas to leak into the heater. To counter that, Nexthermal has developed a special process to completely seal the heater, which is commonly used for medical system requirements for ultra-low electrical leakage to ground and ensure patient safety. For high-temperature designs, a ceramic potting is used, which is rated higher than the permissible heater temperature. In cases where this is used, there's very limited sealing performance, although you might notice a glazing on the surface. This potting is also our standard material we use. This form of function does not require a sealed design. I should note here that modern control systems have a built-in soft start programming which drives the heater during startup by operating in a reduced power cycle. This, however, does not protect from oil dripping or processed gases, so the question of the environment should always be considered. Cyclic movement is likely in many tools. As such, materials must be designed to withstand repeated flexing without the failure of either the insulation or the wire strands carrying power or signals. A careful design will include choices of wire insulation and stranding that promote safety and durability. PTFE or PFA, silicone fiberglass are materials of choice depending on temperature and movement. PTFE and PFA are commonly considered the same materials, as the surface temperatures are similar. However, there are differences in environmental performance. For example, PTFE is rated to 260 degrees C at 20,000 hours of exposure, 300 degrees C at 3,000 hours, and a heat decomposition temperature at 320 degrees C. PFA, in contrast, is rated 10 degrees C less, or 250 degrees C at 20,000 hours of exposure, 280 degrees C at 3,000 hours, and a heat decomposition temperature of 300 degrees C. The subtle difference is still one that should be considered. Wire conductor stranding material is also important, not just alloy for amperage and cracking, but also strand count and size. Flexing performance over time is highly influenced by these. Nexthermal has custom designed our wires to perform over time, giving the customer the highest durability possible. One such customization that we make is with fiberglass wires. Our fiberglass wires are rated to 350 degrees centigrade or 650 degrees centigrade, and do not use the PTFE or mica as an insulation layer, thereby reducing the fraying that is common with those constructions. I should take a moment and discuss wire temperature ratings. UL has listing programs for wire temperature ratings at 250 degrees C and 500 degrees C, so wires are grouped into these limits when they are UL listed. While our wire is rated to 350 degrees C, 100 degrees C higher, under UL they would lower the limit to 250 C to comply with that group. As a result, our wires exceed the UL rating, and in actual service will outperform the environmental conditions of a PTFE or a micro-layered construction. The rated wattage of the heater can change. We say that the resistance is fixed, but it can change the temperature. We will cover that in more detail on the next slide. Changes to the input voltage will also change the output wattage. The heater is a resistive device. Its resistance is set from the factory, and a certain voltage will produce a certain wattage output. For example, if we had a 120 volt, 500 watt heater, it would measure 28.8 ohms. or 4.2 amps of current. Per Ohm's law, if we took and changed only the voltage applied to 240 volts, the resistance stays the same, but the wattage jumps to 2,000 watts and current doubles to 8.3 amps. Power companies can vary the voltage coming into a building by plus or minus 10%, so it's not uncommon to see a 120 volt circuit measuring 110 volts. If we use the 120 volt 500 watt heater at 28.8 ohms and applied 110 volts to it, the actual wattage would be 429 watts or 3.9 amps of current. Another consideration is wiring the heaters in parallel versus series. Series is a voltage divider circuit, so roughly speaking, if you wire two heaters in series, each heater will see half the voltage, assuming the resistance of each are equal to each other. It's common to wire two 240 volt heaters in series to power with a 480 volt circuit. While this is a common and practical way of wiring, there is one risk that should be discussed. If the heaters have unbalanced resistance, they will each be getting a different voltage than a 240 volt plant. This can shorten their life as higher wattage output can exceed the recommended watt density and cause premature failure. The other risk is the voltage potential on the circuit is 480 volts, so if one heater shorts to a closed circuit, the other heater will see 480 volts, resulting in failure. And lastly, the electrical isolation and ground of the heater or wiring circuit might not be capable of holding a marching safety with a potential voltage of 480 volts, causing increased risk to operator safety. An example of this is using a 240 volt rated plug to connect the heaters to a 480 volt circuit. This can play games with future electricians that have to work on the tool and expose safety risks that are unnecessary. As I said, resistance does in fact change based on temperature. There are several different alloys that can be used in electric heating. All materials will change resistivity as temperature changes. Some alloys will have a higher positive coefficient change, so as the temperature increases, the resistance also increases, limiting the wattage as they get hotter. These are used as self-limiting heaters and commonly used in low-temperature applications like environmental management or frost protection. For example, this graph illustrates the difference in heat energy being produced using 80-20 nichrome wire compared to 35-18 nichrome alloy. As the heater temperature rises, power output drops on each. The most stable alloy is 80-20 nichrome over the usable temperature range. The last topic in durability I will cover is the sheath choices. Heaters are primarily made from two types of sheath materials, stainless steel and alloy can upgrade. The difference is in surface temperature as well as corrosion resistance. Stainless steel 304 is good to 450 degrees C. Stainless 321 is good to 800 degrees C, which is the same as alloy 800. In a moist environment, the chromium in stainless steel can absorb the electrons in carbon-based steels and cause breakdown of the carbon, allowing pitting on the surface. Keep in mind that even if you're not using spray dye lubes or flood coolant, that air has humidity, and there is an air gap between the heater and the bore. Many machine parts also have residual oils on the surface that can entrap moisture and cause concerns. Cleaning the machine parts must also be done with care. Parts cleaning solutions can use chlorides or tetrachloroethylene and dichloromethane to remove oils. These compounds will migrate into the heater and corrode the resistance wire over time and heat, causing premature heater failure. Any chemical that ends in an I should be avoided around heaters. It is hoped that our conversation about what efficiency means in the world of heaters and topics of durability were beneficial to you. Continuing the discussion in part 3, we will talk about increasing efficiency with design choices we can make. On behalf of the team at Next Thermal, we thank you for your time. Look forward to seeing you in the next video.